Okay, hi. So yeah, my name is Sylvain. You may know me as TNT for IOC. I'm going to talk about Phosphor, which is accelerating, visualization of spectrum using RFNoC. So I hope that by now you know what Phosphor is. If you have not heard of it, I don't know where you've been for the last 3 days because I've seen it 40 times here. So yeah, it looks like this, basically. And what you may not know about it is some of the details. Okay, I'm going to stick to the screenshot. So there is 3 main elements in that display. You have on the top part what I call the histogram part. That's all the pretty colors that just represent like the statistical density of your signal across frequencies. On the top part as well, you have what I call the spectrum lines. You can't really see it very well in the screenshot, but you have a thin red line, which is the obvious max score, and in the center you have a thin white line, which is just average. And then on the bottom part, you have the classic waterfall display. One of the typical characteristics of phosphor is that every RF input sample that comes from your SDR is going to end up in at least one of these. Which means that you have a very high probability of intercept for short events like bursts and things like that. It's not perfect because if your event is like super short and only lasts a couple of samples, it might end up being between, at the edge of an FFT window. You can solve that with FFT overlapping or things like that, but I don't do that at the moment. That's what makes Phosphor great. Unfortunately, that's also what makes it pretty computationally intensive, especially if you're trying to process hundreds of megahertz of spectrum at once. That's why the original implementation used GPU and OpenCL to accelerate this. If you want to have all the details about all these courses and stuff like that, you can just refer to my GLCon 2013 slide where it's more detail about this course. So now, okay, we know it works for GPU. Why would you ever want to run it on an FPGA? Well, there are several reasons. The first is you might not have a powerful GPU enough. Like if you take an X310 or the GLS radios with all the samples they can bring back to the host, it takes a pretty beefy GPU to process several hundred megahertz of spectrum, and you might not want to have that GPU because if you run a laptop you just can't have it, or you might be on a PC and didn't think of buying a good graphic card. Or you might be on an embedded platform like the E310 that doesn't have a GPU at all. Or you might be on an embedded platform like the Jetson where the vendor didn't decide to publish open cell driver for it. And the other problem with Phosphor is to process all those RF samples, since you're processing them on the host, it kind of implies you need to send them all to the host. That can be a problem as well. Again, if you take an X310, sure, you can have 10 gigabit Ethernet, but that implies that you have a 10 gigabit Ethernet card, and if you want to go, or like on my laptop, I can have 10 gigabit Ethernet. I'm not even sure if there is laptop with 10 gigabit Ethernet at all. So yeah, that's the problem. That's why we want to accelerate this on the FPGA aspect. So, what part exactly did I put in the FPGA? Well, everything that's done in OpenCL does. Which means that all the GL part, which is displaying on the actual screen, things like that, is still done using OpenGL and using the GPU. But this is very light work for GPU. Any GPU that's been out in the last 10 or 15 years can probably do it without any trouble. The one in your phone or in your tablet can probably do it as well. I'm sure you can do it. So yeah, I focused on the OpenCL part and mostly on the histogram part, which is the top part of the display. I didn't focus so much on the waterfall at the moment, mainly because most of the computational load is for the histogram and the spectrum lines, and that's where we can have we can gain the most by using the FPGA basically. You can have some gain in implementing part of the waterfall in the FPGA as well, but not that much. So others. What's the general architecture is that, well, of course, I just I didn't implement windowing or the FFT RFNoC drops for that already, and I just reuse those because it's what RFNoC is all about. It's just reusing stuff and plugging them. So I just take as input, pre-FFT data, and I just compute all the statistics for the histogram inside the FPGA itself. And what gets sent to the host is only the strict amount of information that's necessary to draw the display. And what that means is that the data rate of the FPGA is no longer dependent on the bandwidth you're looking at. So if you're looking at 1 megahertz or even 100 kilohertz of bandwidth, or if you're looking at 200 megahertz of bandwidth, what's coming out of the FPGA is at the exact same rate, and it's only a function of the number of FFT bins you want to look at, the number of power bins you have, and what frame rate you want to refresh, 30 frames per second or 60 frames per second, or whatever you want. And that means that the load on the host, on your laptop, on your tablet, on whatever you want to look at the spectrum on, is quite very low, and the data rate is also pretty low. I mean, we're talking, at maximum 1 or 2 megabytes per second, which you can easily do like over Wi-Fi. So you don't even need an hardware Ethernet connection. This would be like the absolute minimum flow graph you would have in a radio to use RFNoC Fosphor. So obviously it all starts with the radio that just sends samples into the pre-existing window block, then the FFT block, and then it all goes to the RFNoC Fosphor block, which will compute all the statistics and stuff like that internally to the FPGA. And then you have, okay, here starts the output of phosphor. If you notice the color of the block, it's kind of purple, dark purple. It's because it's a byte vector. What comes out of this block is not error samples, it's not float, it's not anything. It's interpreted as bytes because it's a complete custom format. That's not this thing. The only part that's going to actually look at this data is this second block here, which is the QT phosphor display. And this is a standard numeric number. This is not an RFNoC block. It runs on the host. It's just a standard GR-sync block. And it takes as input those binary data, and it knows how to interpret them to actually draw windows with spectral capacity. Then you have a second connection here on the output that goes back to the RFNoC Fosphor block, and that's a dashed connection with a gray color port, and that's messages. And that's because the display, to know at which power level you're looking at, what frame rate and stuff like that, it actually needs to configure the FPGA. And the way it does that, it just sends standard messages to the actual RFNoC Fosphor block that will translate them into control packets and to the FPGA configuring registers and stuff like that. So I'm going to attempt to show you this running on E312 and here, which is powered on. And we'll see how this actually works. So, okay. Okay, so this is the flow graph I'm going to be running on the host on my laptop. It has a lot of elements, but most of them are just not really important. The two important things is basically here you have a ZMQ source, which basically is going to take the data that is from the E312 sent over to a network cable to my laptop through the ZMQ blocks of the radio, and send them to the phosphor display block running on my laptop, and all the control packets are going to be sent back to another ZMQ block that's just going back to the E312. And here you have a bunch of sliders so I can configure stuff, and for each you have external PC blocks so that I can just basically configure the flow graph running on the embedded devices from my laptop pretty easily. I'm going to have to show you the flow graph that's going to run on the E300.
I didn't touch it.
Yes. So here I'm just launching the radio companion on the V300 and just forwarding the fixed connection, which you should have never do because it's a really bad idea. That's the most convenient way to do it. It's good time to do it. Okay, so this is the program that's going to run on the embedded devices. So as you see, I have the radio. In theory, I really should, window my FFT, which just so happens that the FPGA image that I'm currently configured doesn't have the window block here, so I'm just bypassing it and just feeding it directly to the FFT, which again you should never do. Then the RFNoC Fosphor block, the 5.4, and then instead of sending it directly to the display block, because I can't display on the D12, it doesn't have screen or anything, I'm just sending to a ZMQ block, which is just going to send everything to my laptop to be reprocessed. Now, I could actually do all of this over wireless, but the E310 doesn't have wireless built in, and I don't have a wireless dongle, so I'm just using a cable. The data rate between the two is really low. It's going to be like about 1.2 megabytes per second, which would tolerate more over Wi-Fi. So I'm going to start the flow graph on the E300. Good. And here, okay, and this is what the display looks like. So this is obviously the Wi-Fi there. I can try to tune to cellular. Yes. And yeah, so this is the cellular band. Now it's actually a bit more configurable than the original GR Fosphor block. For example, you can change things like the time constant used for the statistics. Like, for example, they're rather slow, which means you don't see the display moving a lot, but you can make them much more reactive by tweaking this. So here you can see more of the burstinator of the signal. So you can see, for example, this is probably CDMA. This is obviously LTE. You can actually see individual suppliers. It doesn't appear very well on the screen. Actually try. I think that's the one that shows better on the screen. And so yeah, it runs. And if I display, for instance, you might not be able to read that very well. But if you look at the CPU load, you can see that my browser is taking 3 volts of CPU, and the flow graph is taking almost nothing. Okay, so what does it do? How does it do this? This is the presentation of what's actually in the FPGA and the internal architecture. As Martin mentioned yesterday in the introduction to RFNoC, if your block is AXI stream input and AXI stream output, it integrates very well. So obviously I just designed it like this. If you have AXI stream at the input, AXI stream at the output, you just take this thing, plug it into the NOC shell, and you have a working RFNoC block. And internally, you just take the data, compute the log power, because the FFT is pretty complex. It goes through something that's called an even-out sequencer. It's just something that's going to ensure some proper timing and some details that are really important. And then you have kind of 4 processes that are going on at the same time, because it's an FPGA, everything is kind of executing at once. You have the computation of the average and max holds. We just reads from the state memory the previous value, computes the max hold and the average value, the new average value, and does the write back. It executes the decay and rise processes. So in Phosphor, every kind of pixel you see on the screen is kind of like a capacitor or kind of like a grain of phosphor in one of the old TVs and things like that, where it charges every time you paint something on it, and discharges all the time. That's what's called the decay and rise process. So the decay is directly applied exponential decay on every pixel on the screen over time, and the rise process, when an FFT is actually drawn on some of the pixel, will apply an exponential rise in them. It obviously has some pretty large internal state to store all this. And the fourth process is the reback tab. And that's what's sending data back to the host basically. While all of this is going on, from time to time, this thing is going to spy on one of the bus and is going to send what's going on that bus to the host, and the host is going to know, okay, this is the fourth line of the display, and I can update my internal copy with the updated value, but control the screen. And this is basically what's decimating heavily the data rate from the input to the output. Then of course, you can 5-fold and some features like that. Yeah, that's what I should explain. Obviously, implementing things in FPGA, you have some challenges. As I said, there's a exponential rise in decay. I'm not going to go over that, but the only thing to retain here is that if you implement an exponential rise in decay in an FPGA and you implement them in a discrete time step, you actually never have to compute any exponential or because all you need is the previous value, multiplication by a constant and addition by a constant. And that's perfect because, for those of you that know Xilinx FPGA, they have ESP48 blocks. That's very much they do multiplication and addition. You have some other complication which come from the fact that when you're doing math on the host, all is well. You have flows and everything. And basically, life isn't perfect, but it's pretty good. When you're on the FPGA, I mean, you could do everything as float in the FPGA, of course, but that'd be pretty wasteful. So everything is done internally as 16-bit values using a fixed point math. That means the quantization effects can show up pretty easily, especially when you start computing logarithm, because if you compute the logarithm of 1, it's a given value, then the logarithm of 2 is actually much higher already. And so you have some power bits in the lower part of your histogram that will never get hit, and that leads to some pretty nasty effect, like you can see here, which you get those bend at the bottom that are really big. You kind of get the same problem when you, for the storage of the internal state of your phosphor state of all of your pixels. You can also store them as 32-bit flows or high number of bits. But I would take a lot of block grams, and block grams are the premium, especially in the E300. And so I've reduced them to only 9 bits. But that means that, again, if you implement the exponential rise and decay on high value, you can see that here your exponential decay doesn't actually decay all the way to 0, which is kind of a problem, of course. And the solution to this, one solution, the one I used, is random number generators. So basically, when I don't have the precision, either because I input as 16-bit or because I only store 8 bits of state, I just do all the computation for the updated value on a much higher precision, like 32 bits or 16 bits or things like that, and I just add all the LSBs that I don't have with the output of random of RNG basically. You need to use a uniform one so that you don't introduce bias. But it makes things much look nicer. If you look here, I just added the two, I did all the math of 18 bits, I just added the two LSBs with RNG, and you can see that basically all the banding has disappeared. And it's a much more correct representation of your signal than this. Your signal doesn't have like a discrete hole over here. And same thing for the control rise and decay. If you look at the green curve here, it's basically similar to the red curve, which is the ideal. So yeah, that's why finally this great case with the input. So what's the current state? Well, it's measured green. It's been integrated for 4 or 5 months, something like that now, in the RFNoC level branch of UHD. It is definitely in the default FPGA image shipped with X300 and X310 if you use the RFNoC branch, of course. It's not yet in the E310, mostly because of resources. But I have some good authority that FPGA is being reworked and resources should be soon freed up. So it might get integrated into the default image as well. There's some arc-coded constant in there that I'd like to get rid of, at least make them compilation option when you build your FPGA discrete. So for example, you can't have more than 1,044 containers. It's also fixed to 64 power pins, that goes to be configurable. The price to pay for this is block grams, basically. If you don't have enough block grams, you could decrease those and lose a bit of power or frequency resolution and spare a few block grams. Or if you want, if you run an X310 and you have tons of extra block grams, I mean, if you look, currently the block uses 25 and an X310 has 795 of them. So you have spare few. You could compute for those 96 points with things like that. So what would I like to do next? I'd like to add one Fosphor. As I said, you can't do that much, especially in data rate, because I think the one where you can have to ship a data back to grow it because it updates very fast. But you can still have some gain, because instead of shipping 16-bit complex samples, which are 4 bytes, you can just ship one single 8-bit value that is already the computed log power and just display that. You can also aggregate several spectrum between them, either using an average or a max load, and just draw the ship and draw the aggregated version of them. And so you can still decrease like 200 megahertz of bandwidth to something that would fit over gigabit internet. And I think that would definitely be useful. I don't know if you may not have paid attention to the spectrum lines. They don't look as good as a large interrupt, mostly because currently I just store 8-bit of precision, that I have to store more of this. Again, the cost is going to be block grams, so it might have to be configurable. Yeah, we teach the context support. What I'd like to do is, inside a single Fosphor block, being able to feed several input signals, basically, and just share the internal memory state between several input signals. The use case for this would be like on the X310 you have two radios. You could look at both radios at the same time, or you could look at one input connected directly at the radio and looking at the wideband spectrum directly out of it, and another input connected to a DDC, for example, and just looking at one channelized detailed spectrum, basically sort of a zoom feature. Internal clocking, it's kind of mixed with what's there. Currently the core is clocked at 200 megahertz, that's kind of low. If you want to support multiple contacts, obviously you're usually at time share your resources, which means that you need to clock them faster if you still want to be able to support 200 megahertz of spectrum. The core has been entirely designed to support much higher clocking than this. I'm pretty sure it will just pass timing at 400 megahertz without too much trouble. I just need to add asynchronous timers and stuff like that so that it gets dropped independently of the controller chip. Another thing I thought of was you can actually reuse most of it for eye patterns because I mean it's just instead of drawing the log power and the FFT spectra, you can just draw your time sample. The only thing is they need to be pre-synced in advance, but so you need that RFNoC for that. There are alternative uses for the core logic that you can think of. So I'd like to say big thanks to Ethos Research for sponsoring the project and my time to work on this. Also to thank the engineering team, especially Martin and Jonathan, for answering all my RFNoC questions. Big thanks to New Radio and everybody that contributes to the project, especially Sebastian and Martin again for the integration of RFNoC in the radio, because it's really easy. I mean, and it's getting easier all the time. The amount of host code that I have to write for this is pretty low. And I was kind of impressed by this, and Martin actually even removed most of it recently due to improvement to the framework. So yeah, and thank you for your attention.
Fantastic talk, thanks. Do we have questions? There you go.
Yeah, awesome work, thanks, always. Some of the features that you put in the tunable features, are they going to move their way back into the normal host GR Fosphor?
Yes, I like the adaptation of the time constants. I definitely want to do that, and also the different profiles. Yes, that I also want to backward. It's actually already an experimental branch on.
And the eye diagrams?
The diagram. Yeah, no. I don't know. Actually, that would be that hard. I never thought about it. But yeah, it definitely work. Of course, the waterfall part would make absolutely no sense. But the other part would definitely. Yeah, that's a good idea.
Any more questions? Sean?
What bandwidth are you sampling with the when you did the E312 demo?
Oh, 16 megasamples per second. Yeah.
Okay. Thanks. And then the other question I had was, oh no, I did one of those. I just forgot.
While Sean thinks about the second question, do we have time for at least one more? No one? Oh, okay, there we go.
Got it. Okay, so instead of introducing noise in the least significant bits, could you actually just do something where, for all your power bins, you dedicate more precision for the lower bits as you go down to the lower levels?
The thing is it's not my choice in the sense that the precision I'm missing is from the output of the FFT log, basically. Internally, all the computation of the log is on 32 bits, which means I have I think the log core log that I implemented is as an output precision of 1 millisecond. And it's just that at the input, if the input of the FFT log is I equal 1 and 2 equal 1, or if it's I equal 2 and 2 equal 2, the result after the log computation is actually skips completely one power bit.
Okay, I'd like to thank Sylvain once again.